So today we're going to start an important lesson, and we will spend more than one lecture. In other words, you should spend more than one typical duration of a lecture on this. So don't go too fast on this one. And we will add probably more examples later on. So this could be a multiple part lecture, depending on how we decide as we move along with questions from the homework and so on and so forth. So this will be about Gaussian elimination, which is a very efficient way of solving linear systems. So it's all about finding an efficient algorithm for solving linear systems. And you will see that some of the steps involved are already known to you. This is really just a matter of understanding an algorithm to put everything together in a very efficient way so that we don't have something to guess through as we move along with each problem. Let's actually start with a 2x2 system, and let's solve it by elimination the way we actually know already. But at this time, I want you to focus on what we actually do with the coefficients at each step, because one of the first simplification to make is to, in fact, track only the change in the coefficients of the system, because that's all that matters at the end of the day. So let's say we have a system with the first equation, 3x minus y equals 1, and 2x plus 4y equals 10. You may say, okay, one of the things we could do to make our life easier, it's true we can actually simplify, I mean, we can eliminate y immediately, but let's just say we want to eliminate x for some reasons. I mean, this is just about standardization, really, as you'll see later. One of the things we could do is, for example, to divide by 2. We can notice that the second row has even coefficients. So if I divide the entire equation by 2, I'm certainly allowed to do that, right? I mean, that doesn't change the solution of the system. That allows me to work with easier coefficients. So the second equation becomes x plus 2y equals 5. Then I can use the second equation, and I can multiply the second equation by minus 3 and add it to the first one. And I can already anticipate something here in the sense that I know that as soon as I eliminate x from the first equation, I'll probably go back. So then if I eliminate x, I can solve for y. I'll probably go back to this second equation to solve for x once I solve for y. So it looks like at the end of the day, when I'm ready to find the second variable, I mean, when I'm ready to find x later on, I'm going to have to use this one. I'm not obligated to do that, but it's probably the one that I'm going to use because it's easier. So let's just put this first equation, this second equation, let's put it in the first position, and let's just keep it with us as we move along. And then, like I said, to eliminate x from the first equation, we multiply the second equation by minus 3 and add it to the first, right? So basically, what we do here, we multiply, like I said, the second equation by minus 3. So it becomes minus 3x minus 6y minus 15. And we add it to the first, which now becomes the second equation. So minus 3x plus 3x becomes 0. Minus 6y minus y becomes minus 7y equals minus 15 plus 1, which is minus 14. It looks like I'm writing more than necessary, but I just want you to focus on how the coefficients change and how the system as a whole changes from one step to another. Then we divide by minus 7, right? The second equation, and that allows me to solve for y, right? So minus 14 over minus 7, that's 2. We're nearly done. Now we go back to the first equation, substitute y with 2, that gives me x equals 1, and I'm done. Okay, so we know already this stuff. What I want you to do now is to focus on how the coefficients change. And notice that we actually don't need, if we want to be more efficient, we don't need to track x and y during this process. What matters are the coefficients of x and y. So already I can write the original system in a much more efficient way by just saving the coefficients and obtaining what is called the augmented matrix of the system. The augmented matrix of the system is simply a table of values, right, with just the coefficients. So I know that x is in the first position, y is in the second position. So let's just write the coefficients, 3 minus 1, 2, and 4. And the right-hand side of the equality, so that I don't confuse it with the left side, let's just write it after a vertical bar. That's one convention of notation. So my original system can be summarized by looking at the coefficients of this augmented matrix. So once again, just to be clear, to the left side of the vertical bar is the left side of the system. And to the right of vertical bar is the right side. So basically the vertical bar signifies the equal sign in a system. Now it's very important to remember that each column gives the coefficients of one unknown. So if you have a 3x3 system, you're going to have 3 rows and 3 columns to the left of the vertical bar. So you're going to have as many columns to the left of the vertical bar as the number of unknowns. Remember, you could solve any linear system with this method with any number of equations and unknowns. It doesn't have to be equal. I mean, you'll see later we could have fewer equations and more unknowns, or vice versa. Okay, let's see what happened from one step to another in our elimination process. So if you look carefully, I can summarize this part here. Okay, so going from this format of the system to this one when x is eliminated by basically tracking some operations on the rows. So first of all, to begin with, let's actually take a step back. To begin with, from the first format to the second, we divided the second equation by 2. So we could say that the first step in the process was to divide row 2 by 2. And that meant the new system had the coefficients 3 minus 1, 1, so the first one is unchanged, and the second row becomes 1, 2, 5, corresponding to the equation x plus 2y equals 5. Then we decided to interchange, because we anticipated that the second equation is the one to use last. So I'm going to put it in the first position, knowing that I'm not going to change it after that. What else did I do? Well, I multiplied the first row by minus 3, and I added to the second row. That's how we eliminated x. So think about before here, we multiply the first equation, or the old second equation if you want, by minus 3, and then we added to the other equation to cancel the x, which means if we look at the coefficients, I used basically row 1 by multiplying the entire row by minus 3 to add to the second row to produce 0, in a sense, to eliminate x from the second equation. So this is basically the most important step, because that's the elimination step. We replaced row 2 by row 1 times times minus 3 plus row 2. We're going to write this in a much more efficient way later so that we don't use that many words, but this is basically the step involved right here. So then the new matrix of the system was 1, 2, and 5. And then after that operation here, the second row became 0, minus 7, minus 14. Okay, so take a look here in the beginning. 0, minus 7, minus 14 will be the second equation. And then, of course, we divide row 2 by minus 7. And then now the augmented matrix of the system is 0, 1, excuse me, this was minus 14, not minus 4. So 0, 1, and 2. So you'll see on the second part of the lecture, this is basically a specific format which is called the raw echelon form of an augmented matrix, or of a matrix in general. It has a very specific format with ones on a diagonal fashion and zeros below them. This is basically the goal, because once in the context of solving the systems, to bring the matrix in that form means to eliminate the necessary unknowns from top to bottom so that you reach to a point in which you can solve the system quickly. This is just a 2x2 system. So now if you go back to how the system looks like in terms of the original variables, the first equation is x plus 2y equals 5, and the second equation is y equals 2. So basically, if you do the row echelon form in the correct way, the last row should give you one solution or one value of the variables you're looking for. In this context, sometimes it gives you slightly less than that, but the last row is the easiest equation, corresponds to the easiest equation. Then once you find, of course, the unknown, you go back like we did before to the first equation, plug the value you found, and solve for the other. So on the second part, I'm going to comment a little bit on the definition of what we mean by row echelon form and row operations in general, but this is the emphasis I want to make in the first part. What we learn is nothing but a systematic algorithmic way of doing what we know already to do. In the 2x2 case, maybe we don't need something fancy like Gaussian elimination, which is this entire process we're talking about now, because you just basically eliminate one variable and find the other one. But as we move along with 3 or more variables, you really need an algorithm so that you are more efficient. So an algorithm of elimination, step by step, that brings you to the easiest possible form over here, and that gives you a way to quickly find the solution, or to decide that the solution doesn't exist, for example, as you will see in a later example. So before we move along with the second part, let's actually make a convention of notation by row j. Let's denote row j by rj. So from now on, when I'm illustrating the row operations, I'm going to just call each row of the matrix r sub whatever the number is for that row. And of course, the numbering, just by convention, is from top to bottom. And with that, let's take a look on the second part on some definitions. You may want to actually print the formula sheet entitled Gaussian Elimination, which I'm going to show you on the next part. But print it so you have it in front of you, because that's going to be easier. So stay tuned. Okay, so let's talk about some definitions and a description of the Gaussian elimination that we will illustrate in the later part of the course. So we mentioned already that we could perform what is called row operations for a matrix, an augmented matrix. Each row, remember, represents an equation. So there are 3 main row operations: interchanging of any 2 rows, replacing a row by a non-zero multiple of that row, and replace a row by the sum of that row and a constant non-zero multiple of some other row. Sometimes these descriptions are a little bit confusing, and oops, sorry about that. Although in practice, once you go over a couple of examples, you actually realize what's the point of each operation. So let me anticipate a little bit to illustrate the point of these operations. So the first one actually is self-explanatory. I mean, if you notice that one row is more convenient to be placed in a different position, you could certainly interchange any 2 rows you want. It's just the order of the equation, so that's allowed. The second one is used to produce a 1 when you need it. When we make that matrix, the row echelon form, the goal is to make the leftmost non-zero entry on each row 1, because that 1 is used as a pivot if you want. It's actually called a pivot in some other algorithms to produce zeros below it. 1 is the most convenient entry for that purpose because you can simply multiply that entry by the opposite of the coefficient you want to cancel. Let's say that's 5 below it. You multiply the 1 above it by minus 5, the entire row above it by minus 5, and you add it to produce 0. So 1 is convenient to make zeros with the row containing it. And the third operation is the workhorse of the algorithm, right? It's the actual elimination process. When you replace a row by the sum of that row and a non-zero constant multiple of the other row, the purpose is to make a 0. That's most of the time the reason you do that. Let's talk about the goal, right? The row echelon form that you have to come up with when you use this method. This is a description of what you have to accomplish. What's not exactly, well, I mean, it's described in the algorithm below it. The end goal is to have, as the description says, the entry in row 1, column 1 as 1. So basically starting with row 1, the leftmost non-zero entry should be 1 and zeros below it. And that is the order you do this stuff. So you produce that 1 by any row operations you want, you make the zeros below it, and then you continue. Then as you move downward, the first non-zero entry should also be 1, but shifted to the right a little bit. And it's going to be automatically shifted to the right because remember you produced zeros below the first one on the first column. What's not maybe obvious here is that once you move downward with the second row, the third row, and so on, you're not supposed to touch anymore the rows above it, because that will undo, as you will see in examples, that will undo the zeros you already create. So for the Gaussian elimination algorithm, let me make it actually smaller here so we can fit it in the same screen here. This is, I'm not going to read the whole thing. I strongly encourage you actually to print this paper, this piece of paper. It's given in the Blackboard as well. All this description is, all these steps are a description of how to produce this row echelon form. It's a top and bottom approach, starting with the first row, make 1 on the first position, zeros below it, move on the second row, make 1 on that position, and then zeros below it, and so on and so forth. And make sure when you're done that your matrix is indeed in row echelon form, which is one of the easiest forms to actually solve the system eventually. So with that in mind, stay tuned for the actual examples following this algorithm. And there will be more examples in the later lectures, but we're going to have at least 2 to focus for now. So stay tuned. Okay, so let's put this method to good use. Once we learn how to denote the rows and how to perform row operations, and once we understand what the row echelon form looks like, let's see step by step how this applies to larger systems, because this is the case in which this method is really important, because otherwise, if you don't have an organized algorithm, things could be far more tedious than necessary. So let's start with the augmented matrix. 2, 1, minus 1, and minus 1, 1, 2, 1, and 1, minus 3, minus 1, and 1, and 0. Purposely from the beginning, I'm going to do more steps than necessary, because you will see later, once you get used to the process, you could do more than 1 row operation at a time, and you should do that as soon as you're comfortable. For now, let's focus, and you should have that in front of you, the guidelines on how row echelon form looks like. The first step is to ensure that the first entry in the first row is 1. So the idea is which row operation you can use to accomplish that. And there's more than one way to do it. The thing is to focus on the easiest step forward. For example, you could say, well, I'm going to multiply So let me write it down just for fun. Okay, so you could say, I'm going to multiply row 3 by, I don't know, minus, let's say 2 over 3. And if I do that, not 2 over 3, that makes it a 1. So, for example, you could say I'm going to multiply, or I'm going to subtract, let's say, row 2 minus row 1. Okay, I multiply row 1 by minus 1 and add it to row 2. No, what I meant is row 1 minus row 2. Sorry, I made it even more complicated than I should be. So you could say row 1 minus row 2, and then you save that operation into row 1. That's not the easiest possible forward, because remember, you also have interchanges, right? I mean, you can certainly do that, because if you do row 1 minus row 2 and save the result in row 1, of course, you can produce a 1 on the top. But the fastest way, or the easiest way, is to make is to take advantage of the fact that you already have a 1 on the second row in the first position. So just the interchange between row 1 and row 2 will accomplish the task of placing 1 on the first entry of row 1. Okay, so once you have the 1 in the position that you need in the first row, then you need zeros below that 1. And you could see why actually you needed that 1 to make the process more efficient. Because to produce zeros, all you need is to multiply row 1 by the opposite coefficient that you need to cancel. So we could do 0 underneath this by multiplying row 1 by minus 2 and add it to row 2. So the next operation could be row 2 becomes the old row 2 plus minus 2 times row 1. So I like to write by convention this arrow to indicate that this is the old rows. These are the old rows. This is the new one. Again, later, once you get used to the process, you could do this in your mind much faster than what I write here. So the new row 2 becomes the old row 2 minus 2 times row 1. So let's actually illustrate how the computation works entry by entry. Later on, again, we could do it in your mind. So let's leave some room so I can show the computation. So row 1 doesn't change anymore. I multiply row 1 by minus 2 and add it to row 2. So I got minus 2 times 1 plus 2. Underneath 2, I have minus 2 times 2 plus 1, and then minus 2 times 1 plus 1. 1 minus 1 here. So minus 2 times 1 minus 1, and then minus 2 times 1 minus 1 again. And let's copy the third row. Okay, so this becomes now 1, 2, 1, and 1. And let's see row 2. If we simplify that 0, which was the goal to begin with, minus 4 plus 1, that's minus 3. And minus 2 minus 1, that's minus 3. Minus 2 minus 1, minus 3 again. And then let's copy again the last row, minus 3, minus 1, 1, 0. Before we move along, I want you to notice that what I'm going to do next, I could have done at the same step. And you should from this point on. So you could have produced the zeros instead of 3 and minus 3 on the same step of the process. Okay, so what comes next is, obviously, we need 0 again instead of minus 3. So I have to multiply row 1 by 3 and add it to row 3. So row 3 becomes the old row 3 plus 3 times row 1. And let's see if we can squeeze this in here. 1, 2, 1, and 1. And let's leave row 2 unchanged. And so now I have 1 times 3, or 3 times 1 minus 3, 2 times 3 minus 1, 1 times 3 plus 1, 1 times 3 plus 0. This is the only time when I'm going to do it that spread out, because all of these computations, try to do them, of course, in your mind so that you don't waste too much time. Right now, I just want to illustrate the algorithm step by step, and then we can do, like I said, more steps, more row operations in one single step. So 3 minus 3 is 0, 6 minus 1 is 5, 3 plus 1 makes it 4, and finally 1 times 3 plus 0 is 3. Okay, important here to understand, from this point on, once you realize the first column, 1 and 0 is below it, you don't touch row 1 anymore, because otherwise you will undo what you did before. So the next step is to produce 1, the leftmost non-zero entry on the second row, produce 1 and 0 below. So then repeat the process with row 2 and below. So from this point on, you only use row 2 and below. Once you finish that, then again you move on with row 3 and below, and so on and so forth. Once you accomplish a column with 1 and 0s below it, then you don't touch that row anymore, because you will undo the previous steps. So notice, from this point on, as soon as I manipulate just the second and the third row, no matter what I do, I won't destroy the zeros that I already produced. Whereas if I still keep on using row 1, I'm going to destroy some zeros probably if I continue the process. So that's why you have to do it in this precise order. Okay, so how do I produce a 1 on the first non-zero entry on the second row? Well, obviously, given these entries, the easiest thing is to just divide row 2 by minus 3. So now my matrix becomes 1, 2, 1, 1, 0, 1, 1, and 1 again. And then finally, we make zeros below this 1, which is just 1, 0 to make. And the only way to do it, because I can't touch row 1 anymore, is to multiply row 2 by minus 5 and add it to row 3. And this time, actually, let's do it in one step. I mean, not just with the computation in our minds. So first row doesn't change, second row doesn't change. Now my third row becomes 0. Let's see, 1 times, try to follow my lead here. 1 times minus 5 plus 5, 0. 1 times minus 5 plus 4 makes it minus 1. 1 times minus 5 plus 3 makes it minus 2. And then finally, to produce on the last row, the leftmost non-zero entry to make it 1, just one little operation, row 3 becomes row 3 times minus 1. And finally, the augmented matrix in the row echelon form is 0, 1, 2, 1, 1, 0, 1, 1, 1, 0, 0, 1, and 2. So try to pause for a moment and look at what you end up with and see that indeed satisfies the definition of the description of the row echelon form. What was that definition? The first non-zero entry on the first row, the leftmost non-zero entry on each row is 1. Leftmost non-zero entry, 1, 1, 1. As you move from top to bottom, the leftmost non-zero entries is shifted to the right. They have to be shifted to the right? I mean, that's important. So that means you basically have a kind of like a diagonal of 1s with zeros below it. That's essentially the easiest form, well, one of the easy forms. There's, like I said before, the reduced echelon form, which I won't get into it right now, which allows you to solve the system quickly. Because now, if you rewrite the system from bottom up, the last equation is z equals 2. Remember, these are the columns for x, y, and z. Z equals 2, y plus z equals 1 will be the second equation. And then x plus 2y plus z equals 1 is the first equation. I'm writing them from bottom up because that's how you actually solve them. Last equation just gave you z equals 2. Substitute it upward. And that gives you y equals -1. Go one step further, up, x plus 2 times -1 plus 1, plus 2, sorry, equals 1. 2 and -2 cancel. X equals 1. So the solution is x equals 1, y equals -1, z equals 2. Okay, so on the last example, we're going to do, like I said before, more than one step at a time, and I'll have further observations to make, so stay tuned. All right, so one more example, again, a 3x3 system. And this time, again, we're going to denote the row operations or indicate them, but let's try to be far more efficient and do as many row operations at each step as possible. So do as many row operations as possible at each step. By step, I mean one matrix to another, one augmented matrix to another. So the augmented matrix is going to be 1, -1, 1, and 2, 3, 1, -1, and 1, 5, -1, 1, 7. And I strongly indicate to actually maybe pause the video and try to do it on your own and then check the computation with me as we move along. We already have a 1 in the right position. We need to make zeros below it, so we could do this by replacing row 2 with the old row 2 plus -3 row 1, and row 3 replaced by the old row 3 plus -5 row 1. All right, so the new augmented matrix, so we do both operations at the same time, 1, -1, 1, and 2. Let's read together. 1 times -3 plus 3 is 0. -3 times -1. And by the way, if you need scratch paper, whenever the computation seems to be too hard to do on your mind, just on a corner on a scratch paper, write it down. You're not obligated to do it in your mind if you need a little bit of attention on paper to do the computation, especially if you have fractions involved, as you'll see later. So -1 times -3 makes it 3, plus 1, then that's 4. Because by the way, if you make a small mistake in the beginning, that's going to ruin the whole thing. So you don't want to rush unless you don't want to rush, period, right? I mean, make sure you write the computation correctly. 1 times -3 -1, that makes it -4. And then 2 times -3, that's -6 plus 1, that's -5. Now, row 1 times -5. -5 times 1 plus 5 is 0. -1 times -5, that's 5. -1 is again is 4. -5 plus 1 is -4. And here I have -5 times 2 plus 7, that's -3. Some of you might have already noticed something, but let's say we don't notice anything special. I'll get back to that. The next thing to do is to make 1. Now notice here, as much as we try to avoid fractions with row operations, because fractions are tedious to compute, to continue with the row echelon form, the only thing to do, since we cannot touch row 1 anymore, is to divide row 2 by 4, sorry. That is the only way to produce the 1 in the right position. So I divide by 4, that's 1 minus 1 minus 5 over 4. And just for simplicity, to make easier coefficients, that's basically optional. You could also divide row 3 by 4, just to make the coefficients easier to handle later. 0, 1, -1, -3 over 4. Okay, so I have the 1, 0 is below, I have the 1, I need to produce another 0 below the second one. And obviously the way to do it is to subtract to add -1 times row 2 to row 3, or to subtract row 2 from row 3. That gives me 0, 0. And notice that if I do that, this is also 0. And here, like I said, we do -1 minus 5 over 4. So -1 times row 2 plus row 3, which is -3 over 4. So that makes it 2 over 4, which is 1 over 2. So when I'm done with the row echelon form, and by the way, to be really in the row echelon form, I kind of have to multiply row 3 by 2, right? Because the definition or the standard way of writing this stuff is to say the leftmost non-zero entry on each row should be 1. We don't need to do actually all these 3 steps at the end, as you'll see later, but technically, if you really want to be picky, the row echelon form should be in that fashion here. And notice that the leftmost non-zero entry doesn't have to be just 1 step further from the right. So as you can see here, the 1 basically is 2 positions to the right compared to the previous 1. These are also called pivots or leading ones, right? What's important in the description of the row echelon form is that the leftmost non-zero entries is 1. So the leftmost non-zero entry should be 1. Now, what is the solution of the system? Well, if you write the full equations now, again, going back to the system, now notice that the last equation is 0x plus 0y plus 0z equals 1, which is 0 equals 1. So of course that's not possible, which means the system is inconsistent. So no solutions. You might remember that I said 0 equals a non-zero number. When you move on with these elimination steps, that's basically the sign of an inconsistent system. And in the context of augmented matrices, it's the situation in which you have basically a row with zeros to the left side of the system and 1 to the right-hand side. Now, here's the last important advice that I want to make. Stop as soon as you realize the system is inconsistent. The whole point is not to waste time. The whole point is to be efficient. And if we go all the way back, I'm going to make a mess here on the page, but that's the whole point of actually doing this on paper. If we go all the way back to this step here, we could have noticed that the second equation is 4y minus 4z equals -5. And the third equation is 4y minus 4z equals -3. So they can't happen at the same time. There is no way to find a solution so that the same quantity on the left is both -5 and -3 at the same time. So as soon as you realize that the system is inconsistent, you don't have to proceed with the row echelon form unless the problem specifically says, here's a matrix, find the row echelon form. If the goal is to solve a system, we obviously stop as soon as we know it's inconsistent. Some of you might have noticed, if you look carefully even from the beginning, you may notice here that if you multiply, well, that's actually harder to see, but if you multiply the first equation by 2 and add it to the second equation, you get the third equation except the right-hand side. So 2 times row 1 plus row 2 gives me 5x minus y plus z, but instead of being set equal to 5, as it should, to be consistent, it's 7. So it's clear that these 3 equations cannot coexist at the same time, because the third one is incompatible to the first 2. Had I put here 5 instead of 7, then this would be a situation where not only it's consistent, but you would have infinitely many solutions. But that's a subject for a later day. So for now, attempt the homework and we'll discuss maybe other examples during office hours. And that's it.